Okay. So today we're going to look at 14-2, which are permutations and combinations. And so you should be on the side here. Why is my board? Sorry I have that in the way, but I think it's the new projector. So let's look at a permutation first. So here's your definition of a permutation. It's an arrangement or a listing in which order or placement is important. In other words, order matters. That's really all that's saying. Order matters. I like to think of a permutation like a hair permanent. Girls don't, and boys don't get hair permanents anymore because you have lovely curling tools now, like ceramic curling irons and whatever else you girls use that, you know, whatever. But in my day and age, the curling irons were atrocious. You really couldn't get a good curl on hair. Like, I could never curl my hair. My hair is too thick. So I would always have a permanent, which means that my mother would have to roll my hair in these little tight curls and then put chemical product on my hair. Would it have made a difference if she had put the chemical product on first and then rolled my hair? It sure would. So order matters in a hair permanent. Think of it that way. Whereas in a combination, order doesn't matter. Don't think of a combination as a combination lock. Don't think of it as that as all. So think permutation, hair permanent, order matters, combination, order doesn't.
Wait, is it hair permanent? Is it actually permanent?
Until your hair grows out. No. It'll relax a little bit, but your hair will remain curly until that grows out and you cut it off. Good luck. All right, so this is the formula that you're going to use for permutation. And you need to know what the parts of this formula mean. So you've got this P, and I'm going to zoom in on that. So you've got this P with this sub N to the left and this sub R to the right. This just means, the N right there, means these are your total items that you have to choose from. Whereas the R here would be the number of items chosen. So if I had a bag of marbles, let's say, and I was choosing 3 marbles out of the bag at a time, and I had 10 marbles in that bag, the 10 would represent the N, the total items that I have to choose from, and the R would represent the number of marbles that I'm taking out. Now the example that I'm using is actually not a permutation, because if I'm taking marbles out of a bag and just looking at them, does order matter? I mean, yeah, I might have a red, a blue, or a yellow marble, but if I switch the order, isn't it the same combination? Same thing as if I had items on a pizza. If I had pepperoni, sausage, and onion on a pizza, and I put in another order just like that, but I said onion, pepperoni, sausage, would it be the same pizza? Sure. So toppings on a pizza, order doesn't matter, so it's not a permutation. Picking marbles out of a bag, order doesn't matter, it's not a permutation. So what are some examples of things where order matters? Say that again. Hot dogs. Hot dogs. Well, let me give you an example. How about a combo lock? Does order matter on a combination lock? If I told you the numbers to unlock a combination lock, but I didn't put it in the correct order, I said, well, the numbers are 5, 4, 3, 2, 1. But it's not that order. I mean, eventually you figure out what it is, right? But if you put in 5, 4, 3, 2, 1, it's not going to open the lock. You have to put in the correct combination. So order matters there. What else?
Algebra.
You know, let's think of real life examples.
Like if you're cooking,
Algebra's not real life.
like if you're baking, like I make these brownies, and you have to put the cookies, then the Oreos, then the brownies. Otherwise, they don't.
Okay, so order might matter in baking. Getting dressed, order doesn't necessarily matter unless you put your underwear on the outside of your pants.
Order
Just
definitely.
saying.
What if you don't wear it?
You're still dressed.
You don't put one. I meant it.
Alright.
Yeah,
You
there's
don't
all kinds of.
Guys, I want you to think in terms of more real. You gotta listen. More real life. I'm gonna help you list them out. How about your PIN number at the ATM?
Oh yeah. Put that
Right? Oops, you can't see that. You didn't tell me that. How about your telephone number? I could have several people who have the same digits in their telephone number, but they're in different orders. I'm going to call a different telephone number. What about lining things up in a row? We talked about that yesterday. Does order matter if I'm lining things up? Does order matter if you're standing in line for tickets? Sure, who wants to? Don't you want to be first in line?
I don't want to be cut.
Okay, that's one.
Most people, if they're standing in line, they want to be first in line. Order does matter. If I stand up, 5 of you up here, and I change the order, and I put you in different places, that's a different order. Remember we were talking about the math club wanting to line up for their picture? And we can have a bunch of different combinations, but a lot of different combinations, right? Each of those combinations of the same math kits, those are all different combinations, so therefore order does matter when you're lining up. So you might want to write that one down. Because a lot of you think lining up order doesn't matter, but order does matter when lining things up. Arranging things on a shelf, order matters. If I chose 3 of you to represent this class on a committee for some reason, and let's just say, okay, we'll choose Kylie, Grace, and Haley Taylor.
Why Grace? She falls
Because Grace
down.
is the funny one.
What?
All right,
Grace
so
falls down. She does a big deal.
you need to listen. You're the strict one. You need to listen. If I change the order of that and I said Haley Taylor, Kylie, and Grace are going to represent this classroom, does order matter in that case?
Yes.
No, it's the same group of girls, right? It's the same group of girls. If I just choose 3 of you out of this whole classroom and I don't give you individual jobs, order does not matter. But now, Grace is the president. Kylie's the listen. Stop, Emily. Stop. Kylie's the vice president, and Haley Taylor's the secretary. Now they each have individual jobs. Grace, would you be upset if I took your presidency away and gave it to Kylie?
Yeah, I'd be pretty upset.
Okay, so she's going to be upset if I change her job. Wouldn't order matter in that case? So you need to write this part down. People on a committee, and this would be the same as if I were having an election. So people on a committee with separate jobs. And that's the key right there, is that they have to have separate jobs. It's not the fact that I chose you for a committee. If I give you separate jobs, then order matters. If I don't, order doesn't matter. It becomes a combination, not a permutation. What about a race? Does it matter who finishes first, second, and third? Sure, if I took the first place finish away from that person and said, oh no, the third place, they really want that first place prize. They'd be a little upset, wouldn't they? So, race or contest winners. And then the last one I'm going to put on here, and this isn't by any means the entire list, these are just examples. How about elected positions? Obviously, our president would be upset if all of a sudden we gave his presidency to the vice president and switch their roles. The vice president might be really happy, but the president's going to be really annoyed, right? So order matters in elected positions. All right, so let's see how this works. So we're going to use this formula here, and what does that look like to you? N with an exclamation point. It's a factorial. So you're going to take total items possible as a factorial, and you're going to divide it by the difference between the total items that you can choose from minus the total items that you are choosing or you're selecting. And then you're going to run that as a factorial. So look at this example that I gave you here. Find the permutation of 6 items taken 2 at a time. Put that down. There you go. And so notice that we have our original formula here. We're placing n. Isn't this n right here? This is your n, and this is your r. So they've replaced the n with 6 factorial. Then in the denominator, you're doing n minus r, so we get 6 minus the 2. 6 minus 2 factorial. What's 6 minus 2? 4. So that's why we're really doing a 6 factorial divided by a 4 factorial. And you need to stretch these out. So 6 factorial is 6, 5, 4, 3, 2, 1. 4 factorial is 4, 3, 2, 1. Can't I cancel all of these with all of those? So really all you have left to multiply is 6 times 5, which is 30. So the answer is there are 30 permutations of 6 objects taken 2 at a time, of whatever it was they happen to be talking about. So if we had 6 people in our math club and we wanted to figure out how many combinations of 3-person committees we could make up, we could have 3 different, and granted, in order for this to work, everybody on that 3-person committee would have to have a different job. We could have 30 different permutations of that committee with just 6 people. All right, look at example 2. A specific program requires the user to enter a 5-digit password. Each of those digits, by the way, is an event. So remember yesterday, Caleb put off the table. Yesterday, we were figuring out the total number of outcomes. So the digits cannot repeat, so that's important. Yesterday we did a lot of repeating, right? And it can be any 5 of the digits, 1, 2, 3, 4, 7, 8, and 9. Are there any digits missing? 5 and 6 and 0, right? So how many digits do we have to choose from? We have 7 total digits, right? So will order matter for a 5-digit password? Yes, so that's why we're using a permutation for this. And so notice that they've got a 7 here for total items to choose from, and we have 5 digits in our password, so that's what we're choosing is 5 items at a time. So you've got 7 factorial over 7 minus 5. 7 minus 5 is 2, isn't it? So that's why we have a 2 factorial stretched out here and then 7 stretched out there. Can't we cancel the 2 and the 1? And then you're left, and this is where your calculator is going to come in handy. Whoops, not the 2. You're left with multiplying 7, 6, 5, 4, and 3 together. And we come up with 2,520 ways to create a password. So what if I needed more passwords than that? What would I have to do? I'd have to add a digit onto my password, wouldn't I? And that way I could have more passwords. Or even better yet, I could then create letters and numbers. A lot of you, when you do passwords, doesn't have to be a combination of letters and numbers. And on top of that, doesn't have to be case sensitive now these days. So, you know, if I put in a capital G versus lowercase g, that's a totally different combination. All right, so look at the exercises below. I would like you to do number 1 for right now. So do number 1 all on your own. Just number 1. I want you to write out your work. And I want you to write out, I want you to put it in its equation form first. In other words, you need to do the, I don't want to just see 3 factorial underneath here. I do want to see you doing 7 minus 4 factorial equals, and then you can go on and show what that actually is. And share with the person next to you what you got. Use your calculator and multiply that. What did you get? Did you get it yet? That's what your work should look like, right? make sure that everything in your denominator cancels with something in the numerator. If you've got something left in the denominator, you didn't do what you're supposed to because you don't want to multiply first and then reduce. So I canceled the 3, 2, and the 1 with the 3, 2, and the 1 up top. That left me only with 7, 6, 5, and 4 to multiply. What did that give you? Where's your calculators? What did that give you? What? 840. So there are 840 permutations of 7 items taken 4 at a time. How does 3 look different? What do you think you're going to do with 3? Yeah, you're going to find this permutation and that permutation and multiply them together. So watch what happens. So for the first one, I'm going to do my work up here. So for the first one, isn't it, here's my n, right? Here's my n. So I get 9 factorial over, and then I'm going to subtract those. I get 9 minus 9 factorial. I'm going to multiply that too. This one I've got 16 factorial for my n over, and then 16 minus 2 factorial. So I end up with 9 factorial over, what's 9 minus 9? 0 factorial, we'll talk about that in a minute, times 16 factorial over, 16 minus 2 is 14 factorial. What's the value of 0 factorial? 1, right? Remember that 0 factorial has a value of 1, not 0. So I end up with, in my numerator, 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1, all over 1, don't I? That's for the first one. I'm running out of room, so the second one is going to be 16. I can't talk and write at the same time. I write the wrong numbers. And then, of course, 14. So that would be the second one, correct? Do you see why I wouldn't want you to multiply all this out and multiply all that out and then attempt to try to reduce? That would be crazy. Can't all of this cancel with starting with 14 all the way down to here? So for the second one, I'm really only multiplying 16 times 15. What does that give me? What do you get? What do you get? 240. So the value of this permutation is 240. I'm going to put it up here. And then the value of this one, and since it's all over 1, don't I just multiply all of this together? Right? So 9 times 8 and so forth. What do you get? 362,880. So I'm going to multiply this to that, right? And I get a really big number. So my final answer would be 87 million. 91,200, right? Bless you. That's a lot of permutations. All right, so then the last one we're going to do on this page is it says a club with 10 members wants to choose a president, a vice president. So we have a president, a vice president, secretary, and treasurer. How many positions is that? 4. 6 of the members are women and 4 are men. How many different sets of officers are possible? Do they make a distinction between men and women? Okay. So so we have how many to choose from? 10 people. How many are we choosing? 4. So wouldn't this be a permutation of 10 items taken 4 at a time? And then we'd have to figure out what is the probability that all officers will be women. How many women do we have total? 6 of the members are women and 4 are men. So for that probability, or that permutation, we would have a permutation, but if we're only choosing women, how many do we have to choose from? 6. How many are we choosing? 4. So once we had this answer, wouldn't we take this, because this would be our favorable, and divide it by that? Our total possible? I'm not going to make you do that, but I wanted you to set up those permutations. All right, so flip this back. Let's look at combinations. So your definition for combinations would be an arrangement or a listing in which order is not important. So order doesn't matter. And then here is your formula. You are going to have to memorize both of these formulas. I will not give them to you on your test. Are the formulas similar? Yes. The difference between this formula and the previous formula is this right here, isn't it? The combination takes away some of the permutations that the combination considers doubles. In other words, if order doesn't matter, then when I was talking about Grace, Kylie, and Haley Taylor as officers, there would only be that one combination possible, right? Versus if I gave them each job, I would have a whole lot more combinations. We'd have, how many kids in this class? Would we say? Yes, we'll go with 20. So just the total possible combinations that I could have just for a committee was 3 of you taken out of 20, right? But then on top of that, if I wanted to figure out how many combinations are total between the 3 of you, how many possible would that be? Wouldn't that be a factorial? Because out of the 3 of the girls, 3 of them could be president, right? Then somebody becomes president, right? Then 2 of them would be vice president, and then 1 would end up being secretary. So it's 3 times 2 times 1. 6. So there would be 6 combinations for those girls if I gave them different jobs. 1 combination if I didn't give them any jobs. So for a combination, I have to get rid of all those extras that don't belong. And that's what this R factorial represents, is getting rid of those extras that we consider repeat combos. So let's look at some different types of combinations where order doesn't matter. So obviously a committee selected where members don't have specific jobs. And then what you're going to see in your homework a lot, and I kind of talked about this a little while ago, would be selecting 6 marbles from a bag of 10. I'm just going to pull out 6 marbles and look at them. Doesn't matter what color or design they are or how I rearrange them, it's the same group of marbles. Order doesn't matter. All right, so then you can see an example over here that if we are to take, so it says a club with 10 members wants to choose a committee of 4 members. 6 of the members are women and 4 are men. So the first question says how many different committees are possible. This is kind of like the one that we were talking about on the reverse side. Only, are each of the people given a specific job? Yes or no? No. So then we have a combination of n items taken R at a time. How many do we have to choose from? How many total? How many total members? A club with 10 members, right? So don't we have 10 to choose from? Oh, they didn't write that down, so let's write this down. So a combination of 10 items. How many are we choosing at a time? wants to choose a committee of 4. Oscar, are you paying attention? You're not even looking. Are you looking? Okay. So we have a combination of 10 people that we're choosing 4 at a time. And so notice that we're following that pattern. So this is your n, this is your r. So 10 factorial is our n. Here's our n minus our r. So 10 minus 4 factorial, what's that actually equal? 6. And then times r factorial again. So times 4 factorial. I'm just following that formula. So how did they get from here to here?
That was not me.
So they didn't show all their work, did they? So think of it this way. This is 10 factorial over 6 factorial times 4 factorial. Which of these two is your bigger factorial? 6. So couldn't we write this as 10, 9, 8, 7, 6 factorial? Did you see what I just did? I'm shortening your work, right? I'm shortening your work right here, and there's a purpose for that. Could you write it out 6 by 4, 3, 2, 1? Sure, absolutely. But then I'm leaving this one right here as a 6 factorial, purely as a 6 factorial, times, now how do you write 4 factorial? 4, 3, 2, 1. Why would I want to do that?
Oh, because then you can cross out the 6.
I can cross out a 6 factorial with a 6 factorial. So it does save you some time on your work, right? And so that's how we end up with this. But they didn't write out the 4 factorial, did they? Well, they should have. So down here, now we have this, the 10, 9, 7, 8 right here. But this 4 factorial is 4, 3, 2, 1, right? Now you have to cancel everything in that denominator. Let's see if I can clear that up. Nope, nope, fuzzy, fuzzy. Welcome to my world. There we go. All right, so I have to cancel everything in the denominator with something in the numerator. What can I cancel the 4 with? The 8. So 4 goes in here once and into 8 twice. What can I cancel the 3 with? 9. So 3 goes in there once, into the 9 3 times. And how about the 2? I have a choice. I could cancel the 2 with the 2 or the 2 into the 10. It doesn't matter. So a lot of you are going to do the 2 into the 10. So really what I'm multiplying out is 5 times 3 times 2. Don't forget the 7. 5 times 3 is 15. 2 times 7 is 14. 15 times 14 is 210. So these are a little bit more work. Just leave that. All right, so then let's look at part B. It says, if the committee is chosen randomly, what is the probability that 2 members of the committee are men? Well, how many members of the committee are men? Okay, so there's 4. Well, in the club, there's 4, right? In the club total, there's 4, because there's 10 members altogether. 4 of them are men. That's going to be important. So look at what they've done here. This is what we did on the other side. We have 4 men to choose from, and it wanted to know that 2 of the members are men, right? So if I have 4 men to choose from, and I only want 2 of them to be men on that committee, I'm going to take 4 to choose from 2 at a time. Order doesn't matter because they don't have a specific job. So I'm going to follow my formula, 4 factorial, that's your n, over n minus r, so 4 minus 2 factorial, and then that r factorial, which is 2 again. And so did they show their work to get to the 6? No. So here, let's do our work over here. So our 4 factorial becomes, what's 4 minus 2? So we have 2 factorial times the 2 factorial again. So isn't this 4, 3, 2, there's no point in me doing 2 factorial, is there really? Over 2 times 1 times 2 times 1. Each of these are your 2 factorials. I don't really have to cancel the 1s out, but I am going to cancel the 2 with the 2. I'm going to cancel that 2 into the 4. So I really have a 2 to multiply and a 3 to multiply. That's how they got the 6. And then we still have to do probabilities. So didn't we find, what are they doing with this probability here? Why do they choose 2 instead of a committee of 4? Because this is slightly different than the last one. So we went 2 men, right? Oh, I'm sorry, this is the women? Right. So 2 women taken out of how many total possible women? 6. So same thing as with the men's, we'd go ahead and do the same work. I'm not going to go through the work for that one. So we've got 15 ways to choose 2 women randomly. And so with your simple probability, so here's your simple probability. We've got favorable over total possible, right? Where'd they come up with 90? Where'd they come up with a 6? So 6 is the number of men, and then what's the 15? The total number of women. So 6 times 15 is 90, so there are 90 ways to choose a committee with 2 men and 2 women, right? And so that's your total favorable outcomes, is that 90. And didn't we come up with 210 possibilities if we didn't care if it were all women, all men, or 3 women and 1 man, right? So we had 210 possibilities total. And then of course we would reduce that. How would you reduce that fraction-wise? So zeros would come out, and then what else? 3 goes into the 9 how many times? 3, and then 7. So, or I would prefer to say 3/7. You would never give me a fraction unreduced. So those would be your 2 answers. Okay, so let's look down below. I want you to do number 1. There we go. And you can use your shorthand if you like. When you get an answer, share it with those around you. Share, share, share. You guys are quiet today. And what? Oh, is that the difference?
You're recording this?
Yes, I am. Maybe I should record you every day.
No, then it won't matter.
Oh, then you get used to it, right? No. Okay, so what'd you get? What'd you get? Did everybody get 35? Okay, so I showed the shorthand notation up here, but note how my work looks. I've got, I'm following my formula right here. Then 7 minus 3 is 4 factorial and 3 factorial in the denominator. My bigger one is 4 factorial, so I just stopped the numerator at 4 factorial so I could cancel those 2 out. And I canceled the 3 with the 6, and the 2 with the 2 up here, because that was my only choice. So that left me with the 7 and the 5. All right, so then now you ought to be able to do the 3 by yourself. Actually, I'm not going to let you do that. Let's not do that one because I want you to do, I want to see if you can set this one up down here. So if you might need to talk to those around you and see if you can set that up. Don't do the work yet, just set up the combinations. So it says a book club offers its members a book each month for a year from a selection of 24 books. 10 of the books are biographies and 14 of the books are fiction. How many ways could the members select 12 books? Because aren't they getting, if they're getting a book a month for a year, isn't that 12 books? So they're selecting 12 books out of how many total are possible? 24, right? Does order matter in the books that you read? It really doesn't matter. Okay, so the first question is start with that one. How many ways could the members select 12 books? So set that combination up. Wouldn't that be your combination that you would write? Okay, so go ahead and figure that one out. This one has a lot of writing, doesn't it? So I clumped it, because we're running out of room, I clumped it a little bit. I did stop the numerator at 12 factorial. So can't I cancel this 12 factorial with that 12 factorial? You should have two 12 factorials in the denominator. And then be careful with your denominator. So I would cancel this 12 into the 24 twice. This 11 into the 22 twice, the 10 into the 20 twice, the 9 into the 18, see a pattern here, twice, the 8 into the 16 twice, the 7 into the 14 twice, and then the 6, So does the 6 go into anything that's not canceled out? No, but what multiplies to give you 6? A 2 and a 3. So if I cancel this 6 out, I'm going to cancel one of the 2's, right?
That's right.
Hi.
How are you?
Good. Did you bring him food?
Yeah, you got me tacos.
Are you kidding me?
You want a taco?
No. Yes. I want one. Thank you, though. Bye. Oh, Josh is jealous. All right. So if with the 6 I canceled, with the 6 I canceled this 2 out here, and then I need a 3. Where can I cancel the 3? Okay, 21 has a 3 in it, 7 times, right? And then the 5, what am I going to do with that? 5 can go to the 15. 3 times, and then the 4. Can't I cancel 2 of my 2's out with a 4? So here's a 2 out, and here's a 2 out. And then the 3, what am I going to do with that? There's a 3 right here, so 3 with that 3. And then the 2 with another 2, right? So here's what I have left. I have a 23. I have a 7, 19, 17, a 2, another 2 here from the 14, and a 13, don't I? Is that it? Did I miss anything? So this is what I'm going to put on my calculator. So I've got a 23, 7, 19, 17, a 2, another 2, and a 13. Did I miss anything? I don't think so. Hopefully I didn't. That's a big number, right? So we end up with 2,704,156. Aren't you glad I'm letting you use a calculator? Okay, so most of your problems aren't going to be quite that large, just saying. Now, Thank you. Sparkly. All right, so then let's talk our way through B. It says, what is the probability that 5 biographies and 7 fiction books will be chosen? So don't we have to figure out the possibility of 5 biographies? So if I'm taking 5 biographies out of how many total possible biographies? Where'd it go? Oh, here it is. So how many books are biographies? 10. So wouldn't this be a combination of 10 items taken 5 at a time? Right? And are we going to multiply that to this combination of the fiction books? So how many fiction books do I have total? Or isn't it 14? 14 taken 7 at a time. So wouldn't I multiply those two together? That would give me my total number of favorable outcomes, and then wouldn't I divide it by this 2 million number? So, all right, so then let's look at your homework. So I'm going to go over a couple of questions on your homework.
Couple of questions, we have 2 minutes.
Pass that over to Grace. That's the taco interruption.
Well, that is like 45 seconds.
Okay, I want to point out something on the back. Let's point out something on the back. Look at number 29. Geometric probability is equal to shaded over total. So you have to find the area of the shaded region and divide it by the area of the total region. So on this particular one, the shaded region here is a square, isn't it? It doesn't matter where I put that square in here, it'll be the same probability. How do you find the area of a square? Length times width, which is 4 by 4, divided by, how do you find the area of a triangle? 1/2 base times height. Isn't my base 22 and my height is 8? So I end up with, can't I cancel this 4 into the 8 twice? And there's a reason why I'm not going to cancel the other. I've got 4 over, what's half of 22? 11. What's 11 times 2? 22. Reduce that, what do you get? 2 11ths. So your geometric probability of shooting a dart and hitting that shaded region is 2 out of 11. You do the same thing for number 28. And then one last one real quick. Look at 26. What's the probability that you select a black marble if a white marble has already been selected? You listen up. You have to consider that you are picking something out of the bag. So how many marbles do you have total in the bag for your first draw? 6. What are you drawing on your first draw? 1 what? And how many black marbles are there? 1. Then you set it aside, don't you? Sit down. How many total are in the bag now? 5. What are you wanting to select? Because that one's gone. So how many white marbles? 2. Isn't that the probability that I'm looking for? All right. Have a good weekend.